So just a reminder that I said last time that if these lectures on metaprogramming are not landing for you, I will not be at all offended if you take yourself out and work on whatever you do. But this is an experiment, and I will not be offended if the experiment doesn't work for you. So I am hoping that it does now, and I want to just briefly summarize where we got to last time. If you remember at the end of last time, so we had built somehow the longhand version of what we want our interval cases tactic to do. And it looked like this. And the reason that we knew it was a good candidate for a tactic was that it sort of seemed to be doing the same thing over and over again. We could tell the implicit algorithm, represented by this tactic. We were starting to focus on that. And then having written this out, what our tactic is supposed to be doing, we also started discussing proof terms and the idea that, for example, when you write obtain h primed vertical line h double primed colon equals some stuff, which is something that we often do when the stuff represents an expression with an or in it. This is a tactic that is producing the proof term. So or dot ln, and then that same stuff and then two new terms fun h primed max to, and then a first gap, which becomes a new goal. And then a second gap, which becomes a second new goal. So this is very much typical of what tactics do. You write a tactic line like this, and it builds for you a proof term, or rather a part of a proof term like this. So that is the basic model that we're working with here.
When you say builds it under the hood, you never see this.
You never see this.
That's what's going to the
That is what is happening in the pilot. So when a proof is finished, it's got a full proof term with no more gaps in it. But along the way, we have this sequence of tactics, building pieces like this and keeping track of the remaining bits to work on that are then worked on by the construction of further proof term pieces. So now that that is settled overnight, does anyone have questions about this basic model? Anything that occurred to them as they were thinking about this yesterday? Yes.
So I guess there's some intelligence in how it finds the orange bits, right, from the blue. Is there I guess here it's looking for a disjunction and then splitting it up after that.
Do you mean finding out what needs to be proved in the orange bits, or actually filling the orange bits with proof terms?
So I guess the orange is the same thing in both sides. It's the output of.
So these are the two new goals that are seen afterwards. So Lean, the program, is doing the task of taking this proposed partial proof term and presenting to the reader or the user, these are the two things you need to work on now, and calculating for the benefit of the user what it is that you're supposed to be proving in each of these two gaps here. So that's a computation that Lean, the program, is doing. So on the other hand, we, the users, will at some point, as we continue to work, write more tactics that gradually fill in these two blanks here. Yeah.
I guess what I was wondering is blue in my mind is something H implies orange box, and then splitting into H prime implies orange box and H double prime implies orange box, right?
Yeah, so at the end of writing this line here, this blue is just to represent that it's the same thing as was sitting there. So at the end of writing this line, the blue is totally filled in. What is left for the user to work on are these two orange blocks here. And just to see that in practice, so here is both the obtain version doing that. Before there was one goal, and the blue box in this case is the OR statement to H4. And then afterwards, we have two goals that are these two orange boxes. And notably, as you can see, in each case, we've got a new hypothesis called H primed in the first case, H double primed in the second case, that have got added to the context by Lean's sort of calculation of what is available at these positions in the process of proof term building. And then just to check that our term actually does the same thing, if I change this to this, exactly the same thing happens, reflecting that basically this partial proof term is what is constructed by the obtain line here. Questions? So there are some formalization communities that are very keen on writing proof terms directly. This is a style you sometimes see. In particular, I think you see it a lot, for example, in Agda and in Rock, particularly Agda, like people who like to work on homotopy type theory and things like that. They often, as a sort of sociological observation, tend to be very keen on writing the proof terms by hand rather than by using tactics to construct them. And their languages have all kinds of automation that are built in to make it easy to write long, complicated sort of nested proof, nested trees of proof terms. Lean doesn't have quite as much in that direction just because we more rarely manipulate proof terms directly and instead use tactics. But there's this sort of cultural difference among different communities of people who use proof assistance. And some of them, including both the Agda and Rock people, and also like, if you look at like 5 to 6 to 7-year-old Lean code from the early days of the Lean community, you'll often see it is more proof term heavy as well. So that's, I guess, where we were at the end of last time. Any more questions before we move on? Okay, so now we need to start actually writing the tactic. And so for that, let's go on to file 1. So we were on phase 0 last time, and now we're on phase 1. So I'll give you a little tour of this file because there's some pieces that I want us to be working on and some pieces which you won't change. So this first part in green is just my explanations. And then the part we will work on is this part here. This is the core method that we're going to be filling in. I'll come back to that in a second. But then at the end, there's some front end stuff. And I don't want to talk about the front end of tactics at all. So this part you can just not touch. It's setting up what we type and how it gets interpreted by the program and sent to our backend. And finally, at the end, there's some tests which you may want to play with. So let's actually start at the tests. I've got some diagnostics turned on. This set option trace.debug true, which means that we can write little messages to ourselves in the code, and Lean will update us on the questions we asked it, and also this show term to see what's being constructed. So as you can see, as a warm-up exercise, I'm not writing an interval cases tactic in the exact form that's in the library. Instead, I'm writing an interval cases tactic. So in the library, you just say interval cases K. And it's got some magic. So it, for example, looks through all the hypotheses to see which ones are upper or lower bounds on K, and it picks out the best available upper bound and the best available lower bound. We're going to say that to start with, we have a dumbed down version of that, where we tell it that this H1 is the lower bound and this is the upper bound that it should be using. So this is an easier form of the tactic for us, to play with at the start, and then later in like phase 2 or phase 3, we write the part where it picks out the best hypothesis. And likewise, it ought to be able to see that H1 is a lower bound of 1 and H2 is a lower bound of 4, but again, that's some sort of pre-processing stuff that I don't want to get into yet. So for now, I'm telling it, you can assume that when you look at H1, it will be a lower bound of K with 1. You can assume that H2 will be an upper bound of 4. And so this more verbose syntax, it's a common trade-off in tactic writing. You as the tactic writer do more work to allow the user to have a more convenient syntax. So we're writing the done version to start with a very verbose syntax where we have to tell the tactic a lot about what to do. So I currently have a cheating version of this tactic, because if you look closely into the implementation, if you look at the term that's being constructed with my tactic, I'm just giving it a sorry. So it looks like I'm doing something clever, but actually all my tactic is doing currently is inserting, sorry as a solution to the problem. And this is what I did to start with so that I would get something that did compile, but that didn't actually have any of the work done. So our task is to stop the tactic from, solving the goal by sorry, and instead actually do what it's supposed to do. So far, so good. Okay, so now comes, I think, the really serious stuff. Here is the piece that we need to modify. And I want to start by just explaining the basic type signature here. So this is the core interval cases algorithm. We have two hypotheses, H-min and H-max. H-min is what's called an expression, that's this capital Q, representing a proof of n1 less than or equal to x. And H-max is an expression representing a proof of x less than or equal to n2. Here, n1 and n2 are natural numbers, and x is an expression representing a natural number. So just let the word expression flow over you for now, and we'll come back to this later. We're furthermore given a goal. This is the thing you're working on proving. And the output of this core algorithm is going to be a list of goals. The reason being that when you run interval cases, we're expecting to start with one goal and to end up with, for example, 4 goals. In the example we were studying last time, we started with the goal of showing k divides 12, and we ended up with 4 separate goals of showing 1 divides 12, 2 divides 12, 3 divides 12, and 4 divides 12. So we're going to get a list of those 4 goals as the output, given the input, which is the goal we started with. So this is a metaprogram. It takes one lean proof state, and it gives you out some collection of other proof states. So far, so good? Yeah. Q, this is the so-called QQ, or quote 4 library for lean 4. We'll talk more about it later on, but for now there's a lean, so the basic expression in metacode in lean is the expression. And this is saying that this thing is an expression, but moreover, we assume it represents a proof of this fact here. Yes?
You already mentioned this, but what is a partial definition?
Excellent question. So the reason I put partial is that I expect it to be a recursive function. Because if you remember what we were writing last time, we had this algorithm where we split on the lower bound, and then we reduced to a smaller problem, and then you split again, and you blah, 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 blah. So when you write recursion in lean, in metaprogramming, lean will generally complain if you do that kind of recursion without showing that it terminates. So that partial warns lean that your function may not terminate. I think at the moment I could delete the word partial and no harm would be done. But later when we actually implement the recursion, it's going to complain if we don't have that partial keyword there. So that will actually be an interesting test to make at the time. At the moment when we first start calling ourselves, remove the word partial and see if it fails to compile.
Absolutely. What happens if you try to use partial inside Mathlib?
Yeah, I mean, I'm not even sure I totally know. Do we have something that stops people from using the word partial inside Mathlib?
Yeah, no, Mathlib.
But like in Mathlib theory.
Doesn't it just all of the other functions that might use that one?
It totally does. Yeah.
I mean, yeah. You're not going to be able to prove anything interesting in a partial function. Yeah.
Okay, so you're saying that Rob says that we just wouldn't be able to get much further beyond using those definitions that have the word partial. So One more comment about this function that we're defining here, this keyword meta m. So meta m is what's called a monad. And what I can tell you with confidence is that I do not fully understand what a monad is, and I can still metaprogram. So I recommend not thinking too hard about it. That is my proposal. So any more questions just about the inputs and outputs of our metaprogram here? Yes.
Why is it called mvar ID?
mvar ID. So this is a identifier for a meta variable, but an mvar ID is a goal. It's somehow the combination of the hypotheses and the goal that you're supposed to prove from those hypotheses, like a full, a full single goal, and they get passed around. So here we have an input of one, and an output of a whole list of them, but you should think of this as a packaged collection of hypotheses plus goal. Other questions? Okay, so you can see, here's what I've got so far as our metaprogram. I say, so here G is the goal, and I get the type of my goal, and that is going to be an expression representing a proposition. So in the example we were looking at last time, the type of the goal would be proving that K divides 12. And then I run this debug code that we can look at later. So we can experiment later with the debugging mechanism. This does nothing except for help us to debug. And then what I do here is I say, use sorry as a proof of this statement T. So T, remember, is in this case, the fact that, in the case we tried before, the fact that K divides 12, but whatever the goal that we're trying to prove is, we say, take sorry to be the proof, the sorry proof of that statement. Then you say, so assigning meta variables means solving the goals they represent. So we're saying, here's how we prove the goal K divides 12. We have the following expression, which is a proof term for that fact. So we assign the meta variable G, and then we return the empty list, because at that point, there's nothing more for the user to do. There are no goals. So this return is supposed to return all of the open goals after everything you've done in the tactic. And in this case, there are no open goals. So these 5 lines here are what I had to write in order to get the tactic to give the sorry proof of this statement. And you can see that one line, the debugging line, is showing up over here when I run the tactic, correctly inferring that the T in this case is the fact that K divides 12. So this debugging is useful. You can turn it on and off with this set option. And we're going to keep it on so that we can send messages to it ourselves. Like, for example, if I wanted to trace not just the T, but also our full goal state, I could do that. Our full goal state, I could ask it to print out G, and let's see what that is. So now the debug mechanism is printing out the whole meta variable identifier represented by G. So it's this collection of the variable K, 2 hypotheses about it, and the task of proving that K divides 12. So that package is the G, and the T is just the K divides 12. Any questions so far? Yes.
Where's like the best reference for the tactics monad API?
I don't know if there's a good reference. There is a book called Metaprogramming in Lean, which is a good book, but takes a sort of more generalist point of view and has only some parts devoted to this kind of thing. There's a new tactic quick start guide, which was released, I think, only a couple of weeks ago. I haven't had a chance to even read it yet, so I can't tell you how it is, but there's probably a link on Zulip if you wanted to check for something in the last couple of weeks.
That's why we're doing this.
Yeah. I, in practice, learned everything I know by watching other people like Rob metaprogram. So I think that this is one of those things where at the moment, like, you know, you just read existing tactic code that is on tactics similar to the ones that you're interested in learning, and you ask a few questions. Like, it's one of those things that's very poorly documented. Okay. All right. So let's talk about the algorithm. We want to do a thing where we work upwards from the n1, sort of step by step. We're going to case split, remember, on whether, you know, x is equal to n1 or whether in fact it's at least n1 plus 1. And then in the second case, we call ourselves to do the whole thing again. That's going to be our basic algorithm. So that means that the first step of our algorithm, well, you know, and it does that, and it does that, it does that, it does that. And then, so at some point it stops. And the reason it stops, you can consult our code yesterday to see why it stops, is that it stops at some point because it's able to prove a contradiction. So we stopped yesterday when the lower bound we had proved, namely 5, was already bigger than our supposed upper bound. That was our sort of base case of the recursion. So we want to do the same thing in our tactic. We want to do a case split on whether we're in the base case or the recursive step. And the way we tell that is by looking at our supposed upper and lower bounds and seeing whether we're actually in the degenerate case where the upper bound is lower than the lower bound. So I'm going to keep all of this exactly the same, but do a case split first into 2 different cases. So if n1 is, so that the degenerate case is when n2 is less than n1. So if n2 is less than n1, then something, and else, then do something else. And I think, let me just sanity check that I've made the right case split here. So we want to be in, this is the sort of base case of the recursion. And this is going to be the recursive step. So I think this is correct. So if we have the supposed upper bound is lower than the supposed lower bound, that's when we have the base case, like 5 less than 4. And otherwise we iterate and run ourselves again. So I think this is the correct dichotomy. Yes?
So like in the $sign syntax in the argument, does that tell me like, look for things like this expression, populate n1 and n2 as appropriate, and then you're able to use n1 and n2 freely in the function body?
So you mean, why do I sometimes use $signs and sometimes not? Or is it a slightly more subtle question?
Maybe slightly more. So I was just asking, like, is the mechanism by which we knows n2 what n2 and n1 are by like inferring it from?
So n1 and n2 are arguments to the function.
Ah, okay, I just didn't see that.
Yeah. Yeah, so in this sort of first relatively easy version of the tactic, we're making the user provide the 1 and the 4. So they'll just get passed along. Yep. Okay, so this is the base case. This is the recursive step. And so at some point, I mean, let's work on this one here. And in this step here, we really want to get around to the point where we call ourselves all over again. This one, on the other hand, will not call ourselves. Instead, we'll sort of observe in this case that we seem to have proved a contradiction, and we'll use that contradiction to close the goal. So those will be the 2 different pieces here. Questions? Mm-hmm.
So there are 2 lines that are repeated in your if then else. So the G assign and return.
Yep.
Could you factor them out?
Well, the point is that I'm going to, in the end, these are placeholders in both cases. So yes, I could, but these are placeholders for like what I'm actually going to do in the tactic. And so I'm leaving them in place. But yes, yeah, that would be fine. If I wanted to take this variable definition outside of that, that would also be fine. And Björn, yeah.
Well, it seems that we could try to cheat by just returning the empty list without having proved anything. So, but will there be an error if we don't assign?
This is a very interesting question, and yes, there would be an error. So let's demonstrate. if I forget to assign one of my variables, that is, if I forget to solve one of my goals, and then I return the empty list to claim to Lean that I solved everything, then the user gets a mysterious error with a red underline. So kernel declaration has meta variables _ example. It's not a very instructive error, but what it means is that the person who wrote the tactic made a mistake in writing the tactic.
So that's the way tactic has to prove that it is equivalent to what it has to do. So
your tactic like starts with a certain thing that it has to prove, a meta variable.
Yeah.
And along the way, it might sort of, you know, say, okay, I can prove that if I could prove this, I could prove those things if I could prove those. And so it can build that chain as it goes. And it has to explicitly fill all the things that it's not presenting to the user at the end.
Why some meta variables are.
Other questions? Okay. So yeah, that's actually a very instructive question. Thank you. Okay. So let's work on the recursive step first. So I think that last time I framed a lemma that I'm going to copy over because I want to use it here as well. That was this theorem here. So I'm going to drag this lemma into my new file. This is the lemma saying that if you have an inequality of natural numbers, then either it's an equality or else you can strengthen it by 1. I'm going to move it into the new file. Maybe right at the start. And I've done something wrong. Maybe I need more imports.
Or something.
Yeah, this is supposedly in mathlib.order.basic. Okay, that seems okay to import. Still doesn't like it.
But not.
Maybe I don't know that the natural numbers are a partial order. Is that maybe the issue? Nat.inst partial order lives in mathlib.data.nat.basic. Maybe I need to import that too. Okay, great. So for those following along, I had to add, probably I only need the second import. No, I need them both. Okay, yeah. Okay. So I needed these two very basic files in Mathlib about orderings of natural numbers. Okay, and in the recursive case, I'm going to want to use this shiny lemma that we developed. So let's show how to do that. So I'm going to say something like let, and I'll give it a stupid name like B Q of, okay, so this is a lemma, and it takes a hypothesis with an inequality as an input. So I'll say, look at that lemma as applied to the hypothesis H min. Okay, so now we start to see the point of this Q sort of illustrated more thoroughly. So the first time we saw the little q, it had a sorry inside, and it was building a proof term consisting of just the word sorry. Now, for the first time, we're putting something a little bit more complicated inside the little q. And what we're building is a proof term which consists of this lemma applied to that hypothesis. So you write it just the way that you would in normal Lean, like if you were really writing out this lemma with a hypothesis next to it like we were doing yesterday. You know, here yesterday we really were writing out the lemma with a hypothesis next to it, except that when you do it inside QQ world, all of the sort of explicit variables have $signs in front of them to tell Lean to sort of go outside of QQ world to see what they represent. So that's a little bit vague, but I think, you know, just like think of what lives inside the QQ as like what you would write in normal mathematical Lean with these $signs around on top of the variables is a first approximation. And so what if I...
This is Q prop.
Well, excellent question. So what if I made by doing this? This here has type capital Q of a proof that either x is n1 or n1 plus 1 is less than or equal to x. And I might even annotate that because I think that's quite useful. So I'll say I've made something of type capital Q of n1 equals x, or n1 plus 1 is less than or equal to x. Did I do that right? Other way around. Okay. So as I think we sort of were implying last time, the whole point of tactic writing is that you build up bits of proof terms for the user. So this is a very good start. We've got this thing which will obviously be a part of any proof term that we need in the end. Like, you know, that kind of thing was definitely appearing in the proof term we were building yesterday. And we've sort of built it inside metacode, ready to present to the user. We can even go a little bit further, right? Because last time we also started talking about how when you have an or statement, you typically want to do obtain on it, which is equivalently, you know, sticking that or statement inside of a bigger proof term involving this or.alim. So I might even go further and take this thing which I wrote and stick it inside a new proof term. So maybe I'll call this, you know, or split, or maybe I'll just call it split or something. And now I'm going to do the same thing again, and I'm going to say let something else be what you get by running the or sort of recursor on this split thing we just built. That's not quite good enough because the or.alim also needs to know what we're supposed to be proving, but we know what we want to build. We know what we want to prove here. We want to prove this statement T, the overall goal. So we can, I think, help lean out in this case by saying that the C you're wondering about is T. Okay, so what have I made? I've now made a proof term.
C is a variable of or.alim.
Yes, right. I did that a little fast. This may be a trick that people haven't seen before, but if you're hovering over a lemma and you want to, it's struggling to figure out a certain variable. So here it could figure out what the A and the B were, but it couldn't figure out the C. I was just saying the C in that lemma is supposed to be T. So this is a useful trick. In general, when you get that particular error message, which I'll show you again, the error message, don't know how to synthesize implicit argument, blah, 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 you can fix by just telling Layton what the implicit argument is. Okay, so let me write out what I've produced here, because that's also kind of instructive. So it's a proof that if I could prove that this part implied T, and if I could prove that the other branch of the or implied T, then I would know T itself. That is what I have built as my proof term here. So now I know if I can fill in this piece, and if I can fill in this piece, then I get the overall goal I'm trying to prove. That's what I've got with my sort of 2 steps of proof term involving the hypothesis and this lemma and this lemma. Questions so far? Okay, so now I need to make new goals corresponding to at least one of these, right? So which of these is going to be a new goal? Maybe both of them, yeah. So here's how I make a new goal in Lean. And I've actually mentioned it down here in case you are wondering about it later on. So this part here says to Lean, you know, let's now present to the user that they should be proving such and such a fact. And, you know, now that we're presenting to the user that they should be proving such and such a fact, we can use the hypothetical result of them proving that to go on with our proof. So we're going to say, we're going to run this. We're going to say, let M1 be the result of running this business on trying to prove that fact. So this is saying, I want a new goal to present to the user that they should prove if they know x equals n1, then t holds. Likewise, I'm going to do the same thing to present to the user that they should prove that if the inequality holds, then the desired goal holds. Okay, so these are meta variables, this M1 and M2. And if you look at their types, so this is exactly something of type if x equals n1 then t. This is something of type if x and n1 plus 1 is less or equal to 1 to x then t. And having made these, we can actually just feed them into this proof term we were busy building up. So maybe I'll go a little bit further. So this is, I'll call this imp. And now I'm going to keep building up my proof term. So by taking this imp and sticking in M1 and M2, have I done that right? Maybe I need to say Q dollars imp. Great. And now what is this? This is a proof of T. Great. So, I mean, it needs some work, but I've built a proof of T, the real way, not just by filling it in with sorry. So that's great. This is actually, I'll just call it PF because that is the thing I want to fill in as the proof of my goal. So as a partial version of the tactic, I mean, what I could do is just I could send back to the user these two things here, and let's try that to start with. I think this will work. So let's say that I just.
Now you can erase the first PF, right? One in line 68.
Oh yeah, totally. Good point. Yeah. And I think I need M1 dot mvar id exclamation mark. So there's a subtle distinction. Meta variables are a kind of expression. Here, I really want the meta variable, so I need to take the expression and run the code to turn an expression into a meta variable. Anyway, so let's test that out and see what happens. M1, M2. So this is saying, now when I run this, I have two goals. So before I had the goal of showing that k divides 12. Now I have the goal of showing that if k equals 1, then k divides 12. And the goal of showing that if 2 is less than or equal to k, then k divides 12. So far, so good. It's not recursive yet, so it's not as strong as we really want integral cases to be, because we want integral cases to keep going and going and going and going and making the appropriate number of goals. This is just doing one step, but still, it works. Yes?
We make the second case say 1 plus 1 instead of 2.
You mean say 2 rather than 1 plus 1?
Yeah.
Yes. So I don't know the best way of doing this. I do know some ways of doing it. Let me show you the way I know. So the way I know is something like I introduced a new variable, let's say n1 primed, a natural number, which is n1 plus 1. And then whenever I have $n1 plus 1, I actually just change that to $n1 primed. So here and here and here, and probably one of these is the one that really matters, but I think that that should be good enough. Let's check that out. Yep. So now I've got the cleaner goal presented to the user of showing if 2 is less than or equal to k, then blah, 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 rather than if 1 is plus 1 is less than or equal to k, then blah, blah, blah. Yes.
Sorry, I'm trying to follow along. Can you go back to the proof of that initial statement at the top about less than or equal to?
You mean this little lemma here?
Yes.
Mm-hmm.
I've copied it down somehow.
Yeah, you may have a slightly different version depending on how you did things yesterday.
Q is not one.
Q is not
Monadic.
Yeah.
Oh, good. Now I have it.
Okay, so I'm not sure whether it makes sense to stare at this for a little bit longer. Maybe here's an interesting question. So what would happen if I change this to a 2 here? Any thoughts? The 1 to a 2.
1, 3.
What was that?
If you try to do it to be the same, but with 2 and 3 instead of 1 and 3.
So you would hope so, but I think that we'll actually get an error. And the reason that I think we'll get an error is because currently the logic of our tactic assumes that H1 is a lower bound for K of 1. And I think that if we break that implicit assumption, then the tactic is going to break. So let's test that and see. Yeah, okay. So when you get a red underline like that, as I said, the red underline in this position means for the user that it's not their fault, it's the tactic writer's fault. And here the issue is that now that we're building a supposed proof term to solve the problem that doesn't even compile, it doesn't even type check. So that's because we've broken this implicit assumption we were using when designing the tactic. Yes.
If we make one, if we replace the other one with the 2 as well.
Say that again?
Like what if we replace this H1? What if we make H1?
So if we, I think that if we change that one to a 2, then everything should be fine. Yeah.
Well,
So we're still like designing in sufficient generality, but it's just that we haven't yet got the clever version where we do that kind of parsing for the user's benefit. Okay, so going back to our tactic. So on one of these 2 goals that we've made, we're supposed to do a recursion. Take a minute and think about which of these 2 goals we're supposed to do the recursion on. Okay, any thoughts? Yes.
It's not about the recursion, but
Oh, sure.
before we were doing intro, right? Instead of having the arrow in the goal.
I missed that, sorry.
When we did the proof by hand, we did intro on both the goals.
You're quite right. So in the proof term that we built before, we did the or.alim part, which we have built in, and also the intro, which corresponds to the sort of fun H primed maps to blah, blah, blah. So we haven't yet built this part of the proof term. We've only built this part of the proof term. Other questions or observations or thoughts about where we want to recurse now? Elif, yeah.
H-min is changing during the process. So in the split case, I think the recursion should be done.
I missed that, sorry.
And recursion should be on the split case, for example, because H-min is changing.
So the recursion should be on one of these 2 goals, right? So these are the 2 goals that we've created. But what we want to do with our tactic is on one of these, we want to keep going and keep doing the same thing again. And so I'm saying, you know, where do we iterate? Do we iterate on this one or do we iterate on this one? M2, I'm hearing. Votes for M1, votes for M2. Okay, yeah, so I agree with those brave folks who voted for M2. This is the one where we want to iterate. So we want to, as Ragram, right? As Ragram said, we want to run an intros here because we've got an implies goal and we want to run an intro to get a hypothesis here. And then we'll have, you know, we'll be in the same situation before, just having the lower bound gone up by 1, and we'll run the whole thing again. So we can actually do that. Let's try that. So how do we run intros? I think I put the method here, mvarid.intro1. So let's try that. Let M2 primed be the result of running mvarid.intro1 on M2. Does it like that? No, it's not that.
Not mvarid.
What was that?
M2.mvarid.
Oh yeah, sorry, thanks. Okay, so dollars only go on things inside queues is a good rule of thumb. Okay. So just for those who haven't seen this kind of dot notation before, this is shorthand for expr.mVarID M2. And so the dots allow you to move the M2 here and delete it from there. And as you can see that process iterates too. I've now got a dot expression here where I can move this to actually live before the dots here. So you'll often see in like, not just metacode, but in like, high quality Mathlib code, like these long expressions of this, dot that, dot that, dot that, dot that, and they correspond to a sequence of applications of lemmas, one after the other. So here I've got M2, an expression, I get its meta variable ID, step 1, then I run intros on that, step 2. And let's actually see what I got. So I'm actually getting two things out, so I'm going to call this slightly differently. I'll call this F comma M2 primed. So let me show you the two pieces. The M2 primed is an mvar ID just like M2. That's why I've given it the same name. And what it is now the goal of proving just T given a hypothesis around saying that N1 is less than equal to X. So it's what you get from taking this problem here, the M2, and running intro, the tactic intro on that problem. And then what is this F? This F is a so-called fvar ID, so a free variable identifier, and that is how to refer to the hypothesis resulting from here inside that goal. So I think I'm now, like this M2 primed is basically back where we started. We're in a position where we can just run our whole selves again. So let's try to do that. So we are going to take our own interval cases tactics, so ourselves that we're currently running. And now we need to fill in for the recursion. So the lower bound has increased by 1. So the lower bound used to be N1. Now it's N1 plus 1. I think we actually called that N1 primed. So let me call it N1 primed. The upper bound is the same as before. It's N2. The hypothesis saying that N1 is less than or equal to X, that's actually now this brand new F that we've made here. So let me feed that in. And again, oh, sorry, I was supposed to provide the X as well. The X has not changed. The F, same issue as before. I think I need to say like F dot fvar or something. Yeah, F expr dot fvar F rather than F itself. Okay. The upper bound is the same as before, so I just refer to H max, which is my old upper bound. And then the goal is this M2 primed. That's what I'm feeding into the new run of the tactic. Okay, so this is my recursion. I run the same thing all again with the increase by 1 lower bound and the proof saying that that increase by 1 lower bound is still a lower bound, and with the goal that has been produced by all this work. And this G here will be the recursive output, so it'll be a list of meta variable IDs. And now what I want to do is just add the M1 to the front of that list. Lean has a special syntax for that. I'm going to say, take the M1 and stick it to the front of the list G. So that's what this : syntax means. I had an existing list of new goals and I'm sticking one more thing in the front. And this should be a full recursion. And I think now if I remove the partial keyword, it should fail. Let's try that. Great. So if I delete the partial keyword now, I get fail to show termination, blah, 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 which means I've written a recursive function and Lean hasn't convinced itself that this terminates. So let's bring it back. And now we can test it. Oh, sorry.
Will it work in principle if here you provide with a termination proof, which, I mean, it's certainly not possible in this very case, but.
I have never, so yes, in principle it should, but I've never tried to write a termination proof for this kind of thing, and I don't know how hard it would be.
That sounds like you're gonna start to hit up against Gödel, trying to prove that the construction of a proof terminates.
I don't feel hit Gödel, but I mean, certainly, like, I feel like the thing that is reducing is somehow the size of the expression you're working on. So like you'd have to, like, maybe you could say, you know, like maybe you could say that you're invariant or not you're invariant, your sort of measure is like the difference between the two natural numbers, and prove a theorem that is reducing each time, and then you could probably get it. Yeah, but I mean that doesn't matter for tactic writing.
No, sure, sure. It was just a question.
Which is very interesting. But yeah, this determination of the recursion, which we usually worry about so much, just doesn't matter here at all.
It doesn't seem like though you have natural numbers. It seems like you have expressions which represent natural numbers.
N1 and N2 are actual natural numbers, so that would be okay.
Oh, okay.
The x
okay.
is an expression representing a natural number, but the N1 and the N2 are actual natural numbers.
What you don't know right now is that in the recursive step, N1 is increased by 1, basically, because that is happening at the expression level.
I did that there though, right? I said N1 prime at line 68. I said N1 primed is N1 plus 1.
Yeah, then actually I think you should be able to make this a well-founded recursive definition without much trouble at all.
Okay, well, exercise for the auditor, but because it will be a perfectly well-functioning tactic, without that, I'm going to skip that. So I saw there were sort of some other questions, but before I take the other questions, let's just see what it's doing in our test case. So here in the test case at the end, it is now generating 4 goals, which is exactly what we wanted. It's generating the goals for the case 1, 2, 3, and 4, and it's stopping at 4 because, you know, after 4, it gets into the position where the supposed lower bound is 5, which breaks the inequality, and so it goes into the base case rather than the recursive step. And if I test this by, for example, changing 4 to 10 in both places, it will produce 10 goals. So everything is looking good so far. I think I had a couple of more questions. Did anyone want to ask some questions? Yeah.
You already said this, but could you say again what make fresh expression is doing?
Say again?
Could you say again what make fresh expression is doing?
Make fresh x for a meta variable q. Yeah. So this is saying make a new goal for the user to prove, subject to the same hypotheses as before, the following fact.
But we haven't added it to the list of. We don't add it to the list of goals, though.
You're quite right. So the M1 we are returning as something that the user should prove. The M2, by contrast, we're operating on by ourselves again. So the idea is that this keeps generating more goals. You can see that each main goal gets, like, maybe it will help if I draw a trace. So I had my original goal of proving it subject to the hypothesis, I guess, k between 1 and 4. And I split into the goal of showing it subject to the hypothesis k equals 1 and subject to showing it subject to 2 between k and 4. And then there I split into showing k equals 2 or 3 between k and 4. And in the first step of the recursion, the one that I'm writing now, I produce this and send it back to the user. And I also resolve this one. And then I call the recursion. And then in the second step of the recursion, I produce this and send it back to the user. And I resolve this one. And then in the third step, you know, it goes on and on and on. And so at the end, what gets presented to the user is all these separate equality goals together with, you know, one final. So at the end of this tree, I have a case where k is between 5 and 4. And I'll need to resolve this goal in its own right by observing that that leads to a contradiction. So this will get resolved in some other way in the base case. Sorry, I've actually forgotten. It was you that was asking this question, right? But so as you can see, since I sort of resolve one goal each time, creating 2 goals, but operating further on one of them, I think I end up like resolving all the goals I need along the way.
And then at what line is the resolving suppose that, or at what line is the goal being resolved?
So it's this G dot assign PF.
Oh, okay.
Yep. So in the top level of the recursion, the like original goal is getting resolved subject to these two sub goals, but then we keep going further on one of them and further and further and further. Other questions? Yes.
So is on line 76.
Yep.
Is there some type of checking performed, or you could assign at that level? Can you assign to G any term, even if it is not the right type?
So Rob is the expert here, but I think the situation is that the elaborator is going to try to assign it. The elaborator is not like, it's like 98% likely to make the correct judgment there, but it might fail. And then there's a further kernel check at the very end. Is that?
You could try it very easily by just changing line 75 to make something that does not have type T.
Yeah, like if I say G dot assign Q of trivial, for example, so this is, a fact, it's the fact that true holds, but it's unlikely to correctly resolve my goal. And it gives this error. Do you see the kernel declaration type mismatch, blah, 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 blah.
This type checking is not performed at the you're too low level.
No, I mean, so in the metaprogram, like the elaborator at this point, like type checking interval cases itself doesn't know what the expected type for the meta variable G is.
Oh, because still a meta variable. Okay, exactly. Because,
yeah.
I mean, if you wrongly type on line 75, then it complains.
Exactly.
Exactly. So
that's because it has like the QQ package has more information.
Fine. Thanks.
Where in the elaboration process will this tactic be run? Like this code actually execute?
Another excellent question. So this tactic is run, and as I understand it, somehow this tactic like produces a term which then maybe gets elaborated and then gets type checked. So I'm also not totally sure.
It's like in some languages, the metaprogramming is like the first thing that happens and just operates directly on the abstract syntax tree. But this doesn't happen that early, right?
As well.
Okay.
Yeah. So I think it's probably time for tea. Let me see. Okay, so we will continue tomorrow with the base case. Right now, it's time for tea. Thank you, everyone.